we have this cameraman image. Let's say that was taken with a camera with focal length 600 pixels. CSCI is in the middle of the image. And we want to find the unit vector, the 3D unit vector in the direction of his eye here. So what I'm going to need to do is compute the normalized image coordinates. So I want, I'll call it Pn, which is the normalized coordinates. Because if I know that, I can find the unit vector by simply taking this vector, there's a little vector here, and making that of length 1. So just scaling it so that it's of unit length. Okay, so we know in order to find the normalized coordinates, I need to multiply by the inverse, I'll say the unnormalized coordinates. The location of the cameraman's eye, let's go ahead and find that. Okay, so that's approximately 126.61. So, and in homogeneous coordinates, that would look like this. My k is 600. I said the focal length was 600. And the center, CXCY, is in the middle of the image. To find out the size of the image, I'll type whose, and this image is 256 by 256. So the center would be 128. Whoops. 128, 128. Okay. All right, so we can go ahead and compute this now in MATLAB. So K is 600, 0, 128, 0, 600, 128, 0, 0, 1. The unnormalized points are 126, 61, 1. So the normalized points is inverse of k times the unnormalized points. Okay, so that gives me the coordinates in normalized coordinates. And I want the unit vector corresponding to that. So it's Pn divided by norm of Pn, that's the length. So it says that the unit vector is 0.033 minus 0.1 and 99. And that kind of makes sense if you look at this picture. It's more or less in the middle from left to right. It's a little in the negative y direction, and then again, of course, mostly in the z. Okay, look at a couple special cases of projection. This is a very useful special case when you take an image of a planar surface and from two different viewpoints. I'll call them camera 0 and camera 1. In this case, and I'm not going to derive it here, but if you want to relate points in the first image, image 0 to image 1, those can be related by a homography, which is a 3 by 3 transformation or 3 by 3 matrix like this. It's in homogeneous coordinates, so we have to divide through by that third element. This is very useful because it's a very strong constraint on the relationship of these points to these points. And I show this in a separate slide presentation. Another special case, actually this is a different kind of projection called weak projection. And this is where you are far away from an object that you're looking at. So if the depth of the object, I'm looking at, I don't know, say a baseball 10 feet away or something like that, the variation within the object is much less than the distance to the object. So if I look at how the points on the object project to the image, the true perspective projection takes x and z for every point, which is different. The weak perspective, the approximation, is to say, oh, I'm just going to use the average z value for all the points. If we do this, it simplifies the projection. So before we had the projection matrix, I had a 1 here and a 0 here. And of course this is k again. Now I have a 0 here and z average here. So the advantage of this is the image coordinates, the resulting image coordinates x, y, are just a linear function of the 3D coordinates. Actually, I should have, this is really just two coordinates, x and y, because z average would be a constant here. So a linear function is a good thing when you're trying to solve for the 3D coordinates, for example, using least squares operation. Kind of combining that now is a special case of a small planar patch. So often we can just model any object as consisting of a bunch of small patches like this. And if we want to track a patch, we want to know how that patch transforms as the object moves. So if the size of the patch is small compared to its distance, we can use this weak perspective assumption. And if the rotation is small, I can use the small angle approximation to the rotation matrix. And of course, I'm assuming the patch is planar. So it can be shown, and I show this in a different slide presentation, that the patch undergoes affine transformation. So if I look at it's a point in image A and a point, then the same point in image B is given by this this transformation matrix. So this is even simpler than homography because it only uses 6 coordinates instead of 9. Okay, let's do another example of perspective projection. So here we have a camera again on a vehicle. We specify the location of the camera and its orientation. And then here this shows where the vehicle is in the world. So this is a top-down view showing that the camera is here on the vehicle. Here is the world coordinate system up here. Okay, so we specify where is the vehicle with respect to the world. It's at 4, -4, +1, and it's rotated by 30 degrees. So say the problem is to observe these points on the ground, 0, 0, 0, 1, 0, 0, 1, 1, 0, and 0, 1, 0. And we want to project those points onto the image of the camera.